thing finished. Okay. So, okay, the next thing is what I didn't get time for these questions. So let's just go through these questions together, okay? So consider the moon falling around the Earth. If the tangential velocity were 0, how would the moon move? So here's the moon, and we're just imagining it now. And if I could just take this away, what do you think would happen? Would it vertically fall downwards, or would it continue horizontally? If you could stop it from moving, you put your hand out and stop it, what happens? What do you think? We'll just do these. We could really do these by voice, couldn't we, almost? But let's just click in. And we'll, is it going to fall down vertically and crush into the Earth, or will it travel horizontally? What do you think? I'm going to stop it there. I'm going to say, well, it's actually split, so I need to do some explaining then. So here we are. It's traveling sideways, and then I stop that motion. I just, boom, stop it. Well, gravity is going to take over, so it's going to fall sideways. So it'll fall vertically like that, okay? That's my intent, okay? The only thing that keeps that away from the Earth is its sideways motion, agreed? Get rid of the sideways motion, I fall into the Earth, just like anything else. According to the equations for gravitational force, what happens to the force between two bodies if the mass of one is doubled? So F is equal to big G, big mass, little mass, over R squared. I think the easiest way to do these is you just turn around and say, okay, I'm only changing one thing. I'm changing the mass of one of the bodies is doubled. So just go around and say times 2 for that guy. If I multiply that by 2, I got to multiply that by 2. So my force is doubled. Agreed? There is a more formal way where I go F new over F old is equal to G new, big M new, little m new over R new squared over G old, big M old, little m old over R old squared. And then when you play with numbers and you say, if I don't know, it's going to be 1. If I don't know the number of it, it's going to be 1. Well, I don't know G, so let's just call that 1, but I know it doesn't change. And I know big M was 1, but now it's 2 because it doubled. Little m, I got no idea about, so let's call that 1. And then my R, I don't know what it was, so let's call it 1 and square it, but now it's still 1 and I'm squaring it. So all that math, and it says, oh, that's 2. So twice the answer. I'm sorry. Okay. So. Can you see how you can intuit it, or you can mathematically do it by math? And some people find one easier and some people find the other easier. According to the equations of gravitational force, F is equal to G, big M, little m over R squared. What happens to the force between the two bodies if the mass of both masses is doubled? Times 2 for that one, times 2 for that one. Can you see how that's going to be quadrupled? Yeah, 4 times bigger. Again, if you get on the test and you're not sure about quartered and quadrupled, doubled and halved, as far as I'm concerned, they're not technical terms, so I'll gladly explain them. If you ask me what gravity is, that's a technical term. You've got to learn that. But for stuff like that, colloquialisms, I try to avoid them, but sometimes I just use them all the time so they slip in. If there is an attractive force between all objects, why do we not feel ourselves gravitating towards massive buildings in our vicinity? Well, is it because there's not enough mass? They are not massive enough, or we are not massive enough, or they are not massive enough, or neither object is massive enough. And it's neither object is massive enough. There is attraction, but you don't feel it because the building's not that big and we're not that big. We feel it with regard to the Earth because the Earth is that big. Yeah.
But if we were big, wouldn't they be gravitated towards us?
Yes, that's right. Both ways. Well, for every force, there's an action and reaction reforce. So me pulling on you is like you pulling on me. Yeah, cool. Yeah, good. How much does the gravitational force between two objects decrease when the distance between their centers is doubled? So then I go F is equal to G, big M, little m over R squared. Now, I'm making that times 2. I'm doubling the distance, but it's times 2 squared. So that gives me times 4, but it's on the bottom. So can you see how that's going to be quartered? It's going to be less because you're further away. And it's not twice, but it's twice squared. So that's 4 times on the bottom, which is quartered. And again, you could do it using that formal way and it would fall out. But most people can see it. In what sense is floating in deep space the same as stepping off a table? You are weightless in both cases, or you are gravityless in both cases. What do you think to that? Will you answer that for me? Can I find my little mouse? When you step off a building, or when you're in deep space, you seem to float anyway. Is that because in both cases you're weightless, or is that because in both cases you're gravityless? What's not there? So what do you think? Oh, flying along. And I'm going to stop it in a second. I'll get it to go to 30 because I'm running out of time. So stop that. And what do most people say? Yeah, most people are saying A. And the fact is gravity is still there. You're still near the Earth. You're not gravityless. You've still got gravity near you in the Earth, but you've not got any gravity when you're out in space. So you've got gravity here, but you're no gravity there. But the fact is when you fall off, you are weightless, and here you're weightless. Because if you stood on a scale, it would read nothing. In this case, it would read nothing because there's really no force pulling you towards the scale. And in that case, it would read nothing because the scale is being pulled down just as fast as you're being pulled down. So we'd say, in that case, that you are both weightless, but you're not both gravityless. We know that both the moon and the sun produce ocean tides. We know that the moon plays a greater role because... I think this is... I'm so sorry about this. Yeah, forget that one. That's out of... Well, we'll answer it. Well, no, we're not. I'm not going to even go there. Forget that. Just forget that one. It's from the wrong chapter. Horizontal rifle. A horizontally held rifle is fired over a level range. That means level ground. At the same instant, a bullet is held at the side of the rifle, is released and drops to the ground. Which will strike the ground first? So here's the rifle, and here's the bullet. Level ground. Which gets to the ground first? Does the fired bullet, or does the drop bullet, or is it both the same? What do you think? Almost there. I'm going to just stop it now. See where we're at. Oh, evenly split. Oh, okay. So remember to divide this motion up into components. So my sideways velocity is nice and steady because there is no gravity. But my vertical motion is affected by gravity. And it turns out that the gravity is in the vertical direction for both the fired bullet and also for the drop bullet. So it has the same effect. So it takes you so many seconds to reach the ground by dropping the bullet. As long as this is a horizontally fired bullet, it will take the same number of seconds to reach the ground. It's just going to reach the ground a lot further away. So, yeah, it's got to be a long, long, long piece of level ground. And it's really got to be horizontal, but they will fall side by side. and they will land at the same time. So I would say for this one, both strike the ground together. And if you didn't say that, then try and think what it was that was throwing you off. Maybe it was this question wasn't clear, or maybe it was something about the thinking about it. Suppose a cannonball is fired at 3 meters per second. How far below the straight line would the path be after 5 seconds? Have I skipped anything? No. So here we go. Okay. So I didn't really go through this, but I'll go through it now. So my distance vertically is equal to minus g times t squared, delta t squared. What it is delta x is equal to vi delta t plus 1/2 a delta t squared. And vi, when you let something go, is 0, so that goes away. And a is g, so it's going to be a 1/2 g squared, sorry. So that's where it comes from. Minus 10, so that's minus 5 times delta t squared. So what we'd say here is for suppose a cannonball is fired 3 meters per second, how far below the straight line? Well, this question is not a good question. It's not clear. So I wrote it as well, this is the sad thing, but I wrote it a long time ago, so that's my... suppose a cannonball is fired sideways at 3 meters per second. Then how far below? What it would be 1/2 times minus 10 times 5 squared, which equals minus 5 times 25, which equals minus 125 meters. So that's kind of like what I'm trying to get at, is it falls a long way in 3 meters, in 5 seconds. It falls a long, long way. Suppose a cannonball is fired at 3 meters per second. How far downrange would it travel in 5 seconds? Oh, well, that's just delta x is equal to v times delta t. It's just your speed times your time. So for that, 3 times 5 is 15 meters per second. That's fair game. I don't think that's fair game. Yeah. Suppose a cannonball is fired at 3 meters per second horizontally. How far downrange would it be after 5 seconds? Sorry, I'm just having to read through this. No. Same again. It would be 3 meters per second. How far? 15 meters. I need to work through this. I'm so sorry. I thought these were fine. I just left them be. I'm going to pause there because we're running out of time, and I will come back and sort my act out.